Okay, today we're going to continue with our talk about set theory, and we are going to look at naming the different parts of a Venn diagram. Right, so naming the regions of a Venn diagram. Right, so let's start off with our easier Venn diagram, or easiest Venn diagram, which is a set with one set A. And as we've said, if we're not, so we're in set A, if we're in here, but if we're on the outside, we're not in set A. And to represent not being in set A, this is known as a complement, right? So regard this as a complement of set A. All right, so no problem there. That's probably quite trivial, but I'll be asking, you'll see why I went back to such a trivial state in a moment. All right, let us go to our probably more typical thing, which is here is set A, set B. And what I'm going to do first of all is actually label the items. I'm going to start from the place where we have the greatest overlap first, and let's call that 1, 2, region 3, region 4. Okay. All right. So if I'm in region 1, I'm going to ask you as the audience a couple questions. So if I'm here, what can I say? So if I ask the question, am I in set A? The response will be, I'm in set A. And if I ask the second question, am I in set B? You will say, and at the same time, I'm in set B. So symbolically, we will write that I'm in set A and B. The intersection sign can be read as an and. All right, now let's go back to our second region, and I'll even color code this in a different color. So region 2. Okay, so if I'm in region 2, oops, let's get some regular ink here. Region 2, I'm asking the question again. If I'm in region 2, this blue region, am I in set A? And the response will be, yes, I'm in set A. Am I in set B? No. And at the same time, I'm not in set B. So if I am in set A, then this part will be, yes, set A. I'm not in set B, I must be in the complement. The word and, A intersected with B complement. Let's keep going. In region 3. Region 3, if I again ask the questions, I'll color code this with a yellow. And we will ask the question, am I in set A? Answer will be no, I'm not in set A. And at the same time, I'll ask, am I in set B? No, well, yes, I'm in set B. So here we have, I'm not in set A, so I'm in A complement, and I'm in set B, so I'll be in A complement intersected with B. All right, the exterior Let's just look at that. So part 4, not gonna give it a different color. And I will ask the question, okay, some of you are insisting, yeah, right. Here we go. So all around the 2 intersecting circles, I've now put in a color. I again will ask the question, am I in set A? And you'll say, I am not in set A. And at the same time, I am not in set B. So using these, along with the and, I'm in the complement of A and or intersected with B complement. So the new Venn diagrams or region of these 2 Venn diagrams are, wow, I've drawn this a bit too small, so let's take that circle out so that I can get a greater overlap and hence fit in my writing. So here's the first thing. This would be A intersected B. A intersected B. Region 1. Region 2, we would have I'm in A and I'm not in B. Region 3, I'm not in A and at the same time I'm in B. And on the exterior, this is I'm not in A and I am not in B. So we are able to complete these. Please remember, or don't get caught, that if you have this same Venn diagram, please recall, or don't get so caught up in the notation that you've forgotten if I asked you to identify or to shade set B, let's say, that you don't just do part of it. Set B would be, oops, let's get a highlighter. Set B would have been all of this entire circle, right? So in this case, what we're seeing is set B is really 2 portions or 2 neighboring parts. Okay. But don't throw out the baby with the bathwater and forget the simple things while you're concentrating on the more difficult parts. All right, let's see how good you are. Let's say that I am going to draw a pretty large Venn diagram that will have all the regions. So I'll just label them. I like starting from the innermost and 7, and out here we have part 8. So if I asked you to, based on what we just did, we could ask you to name the various regions. So if I'm in here, region 1, am I in, well, I haven't given the sets any names yet, so A, B, and C. Am I in set A? Yes, I am. Am I in set B? Yes. Am I in set C? Yes. So I'm in set A, and I'm in set B, and I'm in set C. So it's the intersection of all 3 sets. Let's keep going. If I now go to region 2, oh, I keep doing that. Region 2, which is there. Then take a moment look and decide. Are you in A? Are you in B? Are you in C? And I put it in alphabetical order. So I am in A, and I'm not in B, and I'm in C. Right. Continuing, set 3. Or region 3 rather. In region 3, again, take a moment and ask yourself what's going on. You are in A, and you're in B, and you're not in C. Region 4. Oops. So region 4. There we go. Similar idea. I am not in A, but I'm in B, and I'm in C. All right. Let's go back out to these 3. So I'll give you a moment to figure them out, and then we'll compare. Alright, so region 5, which is here, I am not in A, and I'm not in B, and I'm in C. Region 6, which is there now, I am in A and not in B or C, so in B complement and in C complement. Region 7, similarly, you're only in B, or another way of saying that, I'm not in A, and I'm in B, and I'm not in C. And then finally, on the exterior of all of them, we have region 8, which can actually be written as, what do we have? I'm not in A, and I'm not in B, and I'm not in C. Okay, so this is a simple way of going about and writing separate or single regions on a Venn diagram. Right, before we go any further, however, let us go back to the Venn diagram with two sets. And let's look at something called the De Morgan's theorem. All right, the De Morgan's theorem symbolically will say that the complement of the intersection of A and B is equal to A complement union B complement. And likewise, if I have the union and I take its complement, it would be A complement intersected B complement. Alright. Now, this is almost same as, in a certain sense, it's distribution, but in set theory. If I think of the complement acting on each thing in here, it almost reminds you of the distributive property, particularly with a minus sign, right? Now it's just that when we have the complement acting on a intersection, it gives us a union. But let's look at a method of proving. So we're going to prove the Morgan's theorem. Let's call this A and B. Morgan's theorem, part A, using Venn diagrams. Okay. All right. So what I'm going to do is let's look at the left-hand side. So proof. we want to look at A intersecting B and its complement. Is this equal to A complement union B complement? All right, so let's start off and let's look at the left-hand side. Left-hand side, here's my diagram, here's my set A, here is set B, here's our universal set. If I look at working inside a bracket, A intersected with B, let's say I'll color code that with my green here. Okay. Then if I am looking at working in brackets, so if I now go step 2, and I ask, what is the complement of this green region? The complement, so if instead I ask what is A intersected B complement, it would be the unshaded region that I will now have to shade. Okay. Guess this is checking my fine motor skills here, which are not that fine. Okay. So we have worked out and looked at the left-hand side of the statement that we're given to prove. What we would like to do is look at the right-hand side. Okay. So the right-hand side, which is, let's look at A complement union B complement. Okay. Again, starting off with that Venn diagram. Oops. Let's make a key since there are two separate terms. So here is set A, set B. I am just gonna use the complement of A, we'll put in blue, and the complement of B, oops, need to mark complement of B, we will put in a different color. All right. So let's identify these regions. If I'm not in set A, I'm outside of it. So all of the regions outside of that first circle. All right. Okay. So that's our complement of A, everything outside of circle A. Let's look at a complement of B. It would be everything outside of set B. So yes, some of these regions that were already shaded are again shaded. So having this, we will now consider what's the appropriate thing to do. Look at the symbol. What are we doing? We are joining these together. We're using the union. The union is just bringing together the two sets. If anything is present in either, then in the final solution it will be there. So if we look at set A and set B, then everything, anything that is shaded will be in my final solution. So this is what we have. So when we're asked to prove something using a Venn diagram, you'll be taking a left side, looking at the solution, shading, and you'll be looking at the right side and equivalently shading. And the statement will be true if the two regions are exactly the same. And as we have here, not just because it's in a different color, but in our final answer, anything that is shaded is in the A complement union B complement. So indeed, these two things are the same. So it is proven. All right, so I will leave the second De Morgan theorem for you to work as your homework and show or prove using the Venn diagrams that these are indeed an identity. Okay. All right. What I want to do now is if I write a few sets. So if I said let's shade A union B complement. All right, prior to this, we had looked at naming the regions as I'm in A and I'm in B, or I'm in A and not in B. Now we're examining more of the union. And in doing that, remember the union is a joining of the two sets. So if I had asked you to shade this region, think about it, what would you come up with? Okay. So you may want to pause the video here if you wish. All right, what I'm going to do, and then resume. Okay. Now, in our answer, if we look at set A would have been all of this region. I'm looking at the union. The union is a joining of two sets. So I have A, and I'm going to join it with the complement of B. But the complement of B is everything outside of B, right? Including actually some portion of A. So what I end up with, so if I shaded B complement first, as I seem to be doing here, right, this is B complement, but if I get the rest of set A, then I would have all of this region is what is shaded. And as you can see, it seems to be, and if you think about it by De Morgan's law, this is really A complement intersected B and the complement of that. So working this out, you have A complement complement, the intersection is turned around, B complement, and A complement complement is just A. So it's really, you could have, had I given you the region, shaded, and asked you to identify it, you could have given me two answers, either this or here. But as I said, the question that I asked was to shade A union B complement. If we ask the question, there isn't that much that we can ask with just two sets, I guess. So let's say that I have A intersected, or A union B, let's focus on the union, A union B complement. A union B would have been these three regions. would have been shaded. So if I'm working inside the bracket, A union B was the three regions I'm indicating here. In order to shade A union B complement, it would be everything outside of those three regions. So literally, it's everything outside of the circle. Again, using de Morgan's law, I could have asked, or based on what we were doing, since this is one region, we could have asked, am I in set A, am I in set B? I am not in set A and I'm not in set B, which is really de Morgan's law again, that expansion. Okay. Let's do it a bit more interesting things. So again, just to test if you remember, if I asked the question to shade, well, let's put up two at the same time. We want you to shade the region A complement intersected B complement intersected C, and now let's also do something with a bracket in there, not all intersection signs. All right. So what would you get for the first one? So if I am shading this region, they're all intersections, so I could look at the first two. I'm not in A and I'm not in B. So if I'm not in A and I'm not in B, it could be one of two places, here or there. And I am in C, so I can erase that. So my final region, and even based on what we had done before, would be this one region, one part would be shaded. All right, when we come to the next one, it's almost like doing orders of operations as you would in, say, arithmetic or algebra. Work inside the bracket first. So if I am doing this, let's just look at what regions are B union C. So B union C would be any of these regions that I have. And now, if I ask what is set A is these four regions, or comprises of these four regions that I've put a little cross in. And so now we have to decide, how am I going to put them together? Well, the symbol that we have here is an intersection. We are looking at what is common to both, right? So it has to be common to both of these sets. And the only regions that are, let's see what's going on here. Let's pause. Okay. All right, and the only region that is common to both are these three little regions here. Of course, when I cover it with the highlighter, changes color, so I can't tell. So this is why it's good if you're using some colored pencils, etc., to make a distinction between your symbols, hence my crosses and X's. All right, let's see something else. Suppose instead of putting in the brackets where I had them, I now change the order of the brackets and wrote it as A intersected B union C. So A, B, and C are my set. Let's see what you would come up with. Let's see what you would come up with. So again, we're working inside the bracket first, and that once you've completed that, then you look to the next, look at the symbol that joins both parts together and see what happens. So A intersected B would just have been these two regions. Region C will be any of what I have. Let me go back to my notation of using my x's. And look at my symbol that I'm using. I'm using a union. A union is a joining of the two sets. So anything that is marked will be in my final solution. So my final solution would have all of this shaded region. So I hope that this example has shown you that it's important for you to look carefully at your brackets, follow your order of operations if you wish, and as you go along. All right. All right, let's continue now that we now know how to identify the regions. We know how to label or write these regions symbolically, etc. Let's look at some application. These applications are usually in the form of word problems. And what we want to do, many times these word problems are quite long. And what we want to do is, first of all, identify what we're given. So we typically write it in symbolic language and then use a Venn diagram to see what we have. So for example, here, we are given this question that in a university dormitory of 150 students, 85 take mathematics and 40 take physics. If 40 students take neither subjects, how many take both math and physics? Now this is a typical problem. This is pretty easy or standard, and you've probably done this several times. So let's write the number in the universal set, or the number in the set of everything. This is the first number that we're given, was 150. The second thing that we're given is the set number of people taking math. So I will just use the capital letters for these. Number in math is 85. The number taking physics is 40. We are also, given that 40 students take neither subjects. So if they take neither math nor physics, so in math, and no physics is equal to 40, we're trying to find how many take both subjects. Number taking math and physics is unknown. So let's draw our Venn diagram and see what we do. Alright, so here's M for math, P for physics. So what we can do is, let's call this, let's say that this is X. So the number of persons taking both, number in both subjects is equal to X. So if I put X in here, let's look at what we have. So starting with the greatest overlap region, we can also put this in. That was 40 persons who take neither subjects. And if we are dealing with the universal set, we know that in this total there needs to be 150. All right, since the number taken physics is 40, I can't just put 40 here. Oops. I can't just put 40 in this region. That would be incorrect, because the number of people in physics would include both these regions. So instead, we would write 40 minus x. I've accounted for certain number of people before, x number of persons, and what I'm going to do is those that are unaccounted for, those who take physics only, would be 40 minus x. In a similar vein, number of people or total persons taking math was 85, so I've accounted for x already. So putting that together, left about would be 85 minus x. Alright, we can get an equation. We can sum all the parts. The sum of all the parts, 85 minus x plus x, 40 minus x, and or 40 out here must be equal to the sum of the universal set, which was 150. Getting rid of the brackets, etc., we end up with 165 minus x equal 150, and solving x equal to 15. So if we go back, we can figure out this is 15 students who take both. Does the math work out? If I subtract 15 from here, I would end up with, I would end up with 15 from 85 would be 70. 15 from 40 would be 25. And if I add all of these together, 70 who take math only, 15, 25, and 40, we would end up with 7, 8, 9, 11, 150 students. So I've accounted for everybody. Now, owing to the fact that you are in Add Math, the problems will probably not be that easy or so on. We expect that you would have met this type of problems in your earlier in your career. So what we're expecting, let's look at an Add Math type question. Okay, so here's a more typical problem for us in Add Math, and let's look at what we have. We started out with the same scenario. In our dorm rooms, our universal set, there are 150 students. The number taken math, which we call set M, is 85, and the number taken physics is 40. But that's all the information that we have. Let's look at a Venn diagram and see what we have here. So here's our set of everything. Here's our set M, set P. Okay. Now, unlike before, we weren't told anything about those persons who do both subjects, and now in some miraculous way we are supposed to find out about people who take neither subjects. So before we start, what we can do is we can say let the number of persons who do both subjects, math and physics, equal to x. And we can also say let the number of people who do neither subjects be equal to y. So I have y out here, and here is x. Once I've done that, it should be pretty easy to do my setup. I know the number of persons who take, all persons who take physics. I've accounted for x of them before, so it's just a matter for me to do 40 minus x, and in a similar fashion for math, it will be 85 minus x. So despite the fact, don't get so caught up in doing these problems that you begin to freak out. There are two variables here. What am I gonna do with it? Alright, as usual, we can look at the sum of the parts must be equal to the whole, in that we have 85 minus x plus x the 4 regions that we are seeing on a Venn diagram must add up to 150 students. All right, getting rid of the brackets and combining, we end up with 125 minus x plus y equal 150. If I rewrite this, y is 25 plus x. Okay, what good is this expression? Well, the point about this expression is that I could replace my y here. Sorry, let's put that back in. Let's replace this y. Instead, I'm saying it is 25 plus x. Anybody has any idea now? What can we do? We're asked to find the largest possible number of people taking neither subjects. So if we want the largest possible number of people, we want the largest possible y, right? So let's go down here. So largest y would imply that in order to get the largest y, since the expression or equation rather is y equal to 25 more than x, to get the largest y, I need to get the largest value of x. All right. Now, looking at the diagram, so from the Venn diagram, how do I get the largest value of x? Well, if I go back in here, then if I look at these 2 parts, or well, actually all 3 parts. Now, in order to get the maximum value, I'd have to choose, is it 40 or 85? Well, it wouldn't make sense to be 85. It has to be 40. So x has to be equal to 40 because I can't have a negative number of people, right? So if I chose x to be 40, this part would just be 0. Here I would have 40 persons in the intersection. And over on the math only, I would end up with 45 students. So having the largest x, which is x is 40, that will then imply that implies that my y, which is 25 plus x, is now 65. So 65 largest possible number of students. So this means that 65 students at most will not or do not or would not, sorry, have to check my tenses, would not take both subjects, would not take math or physics. So that's a twist that we can have when we are giving you these problems. That is, not enough information for you to fill in all the regions as we had in, say, problem number 1, where because we were given 4 regions, we could have a single variable throughout. Key idea was that the sum of the parts must be equal to the whole. When we got to problem number 2, it was necessary for us to bring in 2 variables and hence change our process of going through this thing. All right, so it turns out that one variable had to be written in terms of the other, and then based on the questions that are asked, as I said, this is an interesting one, then we could find out whether the largest, or sometimes you have the smallest possible value or values of a particular region on your Venn diagram. All right, what we want to do now is we want to look at a set with three sets in our Venn diagram. Okay, let us look at a problem in which we are dealing with three different sets in our Venn diagram. And so if we read this problem, in a sample of science students who take biology, chemistry and physics, 15 students take all three subjects. 90 students take biology, 80 take chemistry, and 55 take physics. If 35 take biology and chemistry, 40 take biology and physics, and 25 take chemistry and physics, then how many students are in this class? And it's telling us that all students must take at least one class. And that was kind of obvious, but I guess they're really putting the idea forward. So let's extract the information that we have here. As we go through, the first thing that we have is that 15. So the number, I'm using the letters B for biology, C for chemistry, and P for the set of students in physics. So number of persons in biology and chemistry and physics is 15. The second thing that we have is that the number of persons who take biology is 90. The number that takes chemistry is 80. The number of persons that take physics is 55. And then as we go on, we have 35 students that take both biology and chemistry. Number that take biology and physics here, that's where I am, biology and physics is 40. And the number of persons who take chemistry and physics is 25. You might notice that I've kind of put things in a certain way. That is, I've tried to put all those items that have one set together, while those with two sets, I've put in another line, and so on. 3 sets, etc. So it's a little bit of organization, if you wish. All right. So this time we're going to have our 3 sets, and this is A, B, and C. So starting off, I'll do a different pen. So starting off, oops. Okay. So going back, starting off, we can look at our 15. 15 would be placed right in the overlap. Oh, do recall that all students take at least one subject. So there will be 0 on the exterior. Here's my set of everything. And really and truly what I want to find is how many people are in that universal set. Alright, having done that, we've found the place with the greatest overlap or a place with no overlap. Usually those are the 2 places that we would or can put things in. Let's look. If I try to start with one of my sets, set of biology, I would have too many regions. So we don't start with the items that have two sets, or rather one set there, because although it's one set, it covers or touches more than one region. Sorry. In fact, set B, as does any of the full sets in these cases, or as drawn, covers 4 different regions. So let's look at doing 2 sets. If I look at what do we have between biology and I've gotten into such automatic mode that I have put A, B, and C rather than the what is present, biology, chemistry, and physics. Alright, so let's see if we can start again. So we have 15 in the intersection of all three. 15 persons do all three subjects. We are now going to look at the number that does bio and chemistry. It's 35. However, I've accounted for 15 already. So in this region, what I will do is I will have 35 minus 15, and that gives me 20. So 20 students were unaccounted for. If we add these two regions that are shown, we indeed will end up with 35. Let's do the same for the next region, bio and physics. So again, bio and physics, we have 15 persons accounted for of the 40. So again, I will take that region of the overlap, the three circles overlapping, 40 minus 15, that would give us 25. So I would have 25 persons in here. Continuing in the same vein, 25 persons do chemistry and physics. So again, 25 minus 15, I get 10. Alright, so we are slowly filling out some of these parts, and what we now want to do is look at those persons who do, remember this region is called bio only, and it's, this is an aside, this would be the set in B, and you'd be in B and not in C and not in physics. So, right? So that's why it's bio or biology only. All right, we're done with these parts. Those are just my rough work. I'm just trying to show you what's happening. If I now look at, let's do a different color. Hopefully that's not too close to what you were dealing with. Let's stick to that. So we'll use this orange color. And if we are looking at this, we had 90 persons in biology, but I have accounted for a few things. I've accounted for these three regions, 15, 20, and 25. So I need to subtract that, minus 20, 15, and 25. And when I do that, I end up with 90 minus 60, which is 30. All right, do check my arithmetic. Sometimes as I'm moving up here, I may get it incorrect. All right, so we have done that. Let's do the same thing for the number of persons in chemistry. For the entire circle of chemistry, we have 80 students who do chemistry. However, some have been accounted for, the 20, 15, and 10. So that's what? 30, 45 students. So 80 minus 45, and that would give us 35. So we have 35 students who take chemistry only. Continuing, physics only. Again, we have 25 plus 15, so that's 30, 40, and we have 50 students accounted for, so 50 from 55 would be 5. So we have completed all regions on our Venn diagram has been completed with our numbers. So going back to find the number of persons in this class, it would just be the sum of all the numbers that are there. Wow, do I want to write this out, or am I just going to do it in my head? Okay, if I look at the entire, so biology, I had 90 plus 35 plus 10 plus 5. So 40, 50, 140 students. Okay. So therefore, there are 140 science students in this class. Okay. All right. Take a minute and review, look over and see, make sure you understand. Make sure you understand that when we're dealing with three sets, we start from a place of convenience, the set of, or the center where all three overlaps, and then it's kind of taking a difference as you go through.